a rational function is a ratio of two polynomials. Whatever polynomial and whatever polynomial in the denominator, that is a rational function.
Question, do both polynomials have to have the same degree?
No. No. So let me give a couple of examples. If there is no x in the denominator, that is not a polynomial, that is not a rational function. Something like this. F of x equals x over 2. This is linear. So a rational function has to have x in the denominator. Otherwise, it's not rational. Okay. I have divided these rational functions in three different types, three different categories. You're not going to find them like that in any book. But I had to divide up into three different categories because only these three categories that I will present to you can be looked at in this class. Even in calculus, to be honest, we cannot really look much beyond type 3. Okay? We need a calculator. We need a computer, a software. That's what I'm saying. So type 1, I'm going to give a few examples, and then you'll tell me why those are type 1. So here's an example. I'm going to say f1 of x plus 1 over x minus 3. I'm going to call the next one f2 of x squared minus 1 over x squared minus 4. And I can continue with another example. What do you notice in these two functions? And why do you think these are of one particular category? The number is not important.
Because they're binomials. Right.
Awesome. So this type 1 is a function that has degree n in the numerator and degree n in the denominator. That's it. That's the reason why they are grouped in one category. Awesome. Thank you. Here's another example, and now this is for type 2. F1. F2 doesn't matter really. F2. Okay, so what do you think about type 2?
Well,
Let me give you one more example before you say anything, because I think I already heard the wheels turning. Minus 8.
well, for one, different degrees.
Correct.
2, you have certain parts of the polynomials missing, like with the x third, you don't have
No, that's not
a problem.
Is that
No.
because like x is technically, I mean that's x is 0? I mean, if it was like 2, could you say 2 over x? Is that still a rational function? 'Cause you said it's
Absolutely.
polynomial.
Absolutely. Absolutely. As long as it has x in the denominator, it's a polynomial function.
Okay, it doesn't have to be numerator and denominator,
Okay.
just denominator.
Just the denominator. Yes. At least the denominator. Correct. So what do these three functions have in common?
And this is one part of it, but I think there's more to it than that.
Well, obviously, we're talking about degrees. Once we establish this in type 1, we have to look at degrees.
Mhm.
That's what it is. Yes, please.
The degree in the denominator is greater than the one of the
That's all I need. Thank you very much. So for type 2, in f of x, degree n, and the denominator has degree greater than n. So if the top is 5, the bottom has to be at least 6. If the if the top is 0, the denominator has to be at least degree 1. Okay, very good. Type 3. Awesome. Thank you. Well done. So now let's look at type 3. F1, x cubed plus 1 over x squared. Another example, x to the 4th minus 16 divided by x cubed minus 1. And I can go on, and she's here, finally. We couldn't do anything without you. We just messed around. Sorry. Just kidding. Okay, so what do you notice here?
It's the inverse or opposite? I'm not sure which, but either way, instead of the greater than n being on the denominator, it's in the numerator
So the numerator has a higher degree
than n.
than the denominators. Okay, but by how much higher? This is
1.
exactly. That's the key this
Mm.
time. So in type 3, f of x is degree
n plus 1.
n plus 1 and degree n. Exactly by 1 unit higher in the numerator than the denominator.
I'm guessing that what you were saying earlier about how we couldn't really cover anything beyond this in this class is something like n plus 2, right?
By n plus 2 you mean?
N plus 2 in the numerator, right?
Numerator is 2 degrees above the denominator.
Yeah.
Yes, we cannot. And the reason is, we can't. But we have to use a calculator for almost
Okay.
everything.
Right.
But that's not my point here, right? That's not why we're doing it.
I was just
But
making
it's
sure.
possible, right?
It is possible,
Okay.
of course. But if the numerator is degree 4 and the denominator is degree 3, what would be the quotient? What would be the degree of the quotient?
1.
Exactly. When you think about degree 1, what function do you have in mind?
Linear.
So that is the crucial item for
So
number
that you
3.
can reduce it down to a linear function.
No, I'll tell you what that
Hold on.
means. I'll tell you where that line
Okay.
comes into play in a minute.
Okay.
But if the degree has power 4 and the degree of the bottom, the top is degree 4 and the bottom is degree 2, then I don't have a line. The quotient will not be a line. The quotient will be something else.
That's what I meant.
Right. And we'll see what happens. Okay. So like with polynomials, we have a long list of things that we have to worry about when graphing a rational function. Here's the list for graphing. Like before with polynomials, if you remember I said the first example will take like forever. The second one will take 3 minutes, and the next one will take 2 and less. Okay? So it's going to take a long time for us to identify everything here. Okay? So number 1, of course, domain. Number 2, x and y-intercepts. X-intercepts. And in parentheses, I will write, of course, multiplicities as well, if any. Number 3, y-intercept. Number 4, something we haven't discussed yet, vertical asymptotes. This is new. Number 5 is also new, behavior of the function, of course, near, and I'm going to abbreviate vertical asymptotes at VA. Behavior near VA. Number 6, horizontal or slant asymptotes, or asymptote, I should write. 7, and behavior. 8, symmetry. That's not new. And 9, max min. And in this case, we will use a calculator many times. Unless it's a term, I know it's a term. And that will be clear. So let's talk about the new things here.
Sure,
Domain.
I don't know a lot about this function.
Yes, we will know a lot about the function. I agree, a lot. So domain, X-intercepts, Y-intercept, symmetry, max min, they're all clear. And behavior should be clear, but it's really not yet clear. These two go together, and they can be accomplished in one step.
Wait a second, we don't need to know the range.
Oh, yeah, we can add the range. Okay, so these two go together, these two go together. So I like to talk about vertical asymptotes. And I would like to start with an example. So let's say f of x equals x minus 1 over x plus 4. Is this a rational function?
Yeah.
Good. What type is it?
Type 1.
Very good. Which means if it's type 1, it means that we know that the degree of the top as well as the degree of the bottom are the same. Is that okay, everyone? Okay, perfect. Like before with polynomial functions, I strongly recommend the following chart. I accept another chart if you invent your own or somebody teaches you in a different way. I'm fine. Okay, I'm going to ask you about the domain. What is the domain of this function?
All real numbers.
Negative infinity to 1? No, 4. Negative infinity to 4, parentheses.
Why would I exclude 4?
It's the denominator. It's a denominator can't be 0.
Negative 4, right? So negative infinity, negative 4, 0 must be in the chart. And what would I write under negative 4?
Parenthesis. Right?
In other words, you're saying nothing. There is nothing I can write under negative 4.
Yeah, you're excluding negative 4.
Exactly. Is everyone in agreement with this? With a domain meaning all real numbers except negative 4. Any questions on that? Are we okay? Perfect. So negative 4 cannot be accepted because if you ask me, evaluate this function for negative 4, I'll say, sorry, I can't give you a number back.
Because you'll be dividing by 0.
Perfect, because I will be dividing by 0 and that's undefined.
Yep.
Perfect. Because the rational function is undefined at negative 4, something very special happens there, which is a vertical asymptote, a line that cannot be crossed by the function. That will be x equals negative 4. So I will write right here under this bar, or whatever you want to write, undefined, whatever you want, x equals negative 4 is a VA, vertical asymptote. So when I graph this function, I will have a vertical line, a dotted line. It's not part of the graph, like the axis of symmetry, but that's not, there is no connection, right? I'm just saying that when we graph a parabola and we graph its axis of symmetry, that's a piece of the graph that is not part of the graph of the function, right? So the same thing here. When I graph functions with asymptotes, I must graph the asymptotes first. So because this function is undefined at negative 4, x equals negative 4 will be a vertical asymptote. Now the question is, once I say, so that is this piece, vertical asymptote. Since the function is undefined at only one x value, it happens that it has only one vertical asymptote. What if the function is undefined at negative 5 and at 2?
That's 2.
It will have 2 vertical asymptotes. But in this case, we have only one. Good. Now, what happens? Because this is the next part, the behavior of the function near the VA. So this is the vertical asymptote. What happens left and right? What is the behavior of the function left and right of the vertical asymptote? There are 4 options. Here's one option. Both sides go to what?
Infinity.
Infinity. Here's a second possibility. Both sides next, left and right of the vertical asymptote go to,
Infinity.
okay. Here's the third option. Your left side, your right side goes to,
Infinity.
and your left goes to, and here's the last option. Your right side goes to negative infinity and the right goes to positive infinity. So once I write x equals -4 is a VA, my next step is this. What I don't know at this point is the sign. I know there are 4 options. 1, 2, 3, 4, but I don't know which one. It's only one out of those 4. What I'm going to do is on the left-hand side of -4, I'm going to pick a number as close as possible to -4. I'm not going to put in the chart. I'm not going to plot that point. But I'm going to write -4.1 and -3.9. I will be using these numbers to identify just the sign of the infinity. So please bear with me. Let's do this together. When I plug in -4.1, what is the sign of the top? Just a sign. When I plug in -4.1 in the bottom, just the sign. Good. 2 negatives, when I divide them, I will get, that's it. That's how I identify what happens or the behavior of this function on the left-hand side of the asymptote. Please plug in -3.9. -3.9 minus 1, just the sign.
Negative.
-3.9 plus 4, just the sign.
Positive.
Good. At this time, I'm dividing a negative by positive. So what is the sign on the right-hand side?
Negative.
Negative. So that's why I'm saying these two go together, the vertical asymptote and the behavior near the vertical asymptote, or vertical asymptotes. Okay. You gave me the domain by simply telling me that the function does not exist at -4. You told me the domain. We discussed the vertical asymptote and the behavior near the vertical asymptote. Now I would like to find the x-intercepts. This is a ratio. How do I find the x-intercepts for any function? Forget about the fact it's a ratio. I should have not said that just yet. So how do I find the x-intercepts for any function? I set it equal to 0. Awesome. When is a ratio 0? It's a ratio. It's x minus 1 over x plus 4. When is this ratio 0? Exactly. Only when the numerator is 0. Because if the denominator is 0, we are in trouble, right? So when is that numerator 0? When x is
1.
Excellent. Be very careful how you position all these x values. They have to be in ascending order. So you cannot place 1 somewhere else, right? Good. So we're done with the x-intercepts. There is nothing else. Now I want the y-intercept. How do I determine the y-intercept for any function, including this one? Awesome. Very good. So here it is. X equals 0. How much is y? -1/4. Very good. So we accomplished this as well. So now I am interested in this. Before I give you the shortcut, I would like you to bear with me and follow my explanation. Let's say I have 1 divided by x. Like, for example, I want to divide a cake, a whole cake. And I want to divide it by 2, so 2 people will get half. By 3, by 4, by 10, by 1,000,000. So when x approaches infinity, when x goes to a big, big, big number, and let's say I start in Asia where the population is more dense. By the time I get to Tom's door, how much will I have left for you from the cake?
Not a lot.
Nothing.
Pretty
Right?
much.
Nothing. So when I divide a small number by a large number, the tendency is that I have nothing at some point in time, quite soon, right? So keep that in mind, and then I would like to discuss this. So x minus 1 over x plus 4. One more time, please tell me what is the degree of the top? 1. So let's factor out the degree. Don't get appalled just yet, bear with me. What is the degree of the bottom? The degree. 1. So let's factor out the degree. How many terms are left in parentheses? I started with how many terms? How many I have to have in parentheses?
1, 2.
If I say 1, then when I multiply x by one term, I will not get those 2 terms back, right? So if I start with 2 terms, I have to end with 2 terms. Good. So x multiplied by what is x?
1.
Awesome. I have to copy minus. So now this quantity multiplied by x has to give me 1. Awesome. Excellent. Please do the same thing for the denominator and tell me what to write.
1 plus 4 over x.
Awesome. I'm going to simplify x with x. And now I'm going to ask you what I just asked you a minute ago. As x approaches infinity, grows without bound, where will this go?
To 0.
Thank you. Where 4 cakes will go?
0.
Still 0. So this whole thing, what is left? Before you say something, just look at it and see what is left. Where will this whole thing approach? 1. So that is the end behavior of this function. So as x approaches infinity or negative infinity, it doesn't matter. This whole function will approach 1. What does that mean? It means this, that as x goes to infinity, the function will do whatever, but eventually will get closer and closer,
Horizontal asymptote.
closer and closer to 1. On the other side, we'll do whatever, we'll figure it out together, but it could come from below. It will eventually approach 1 from below or maybe from above, not both. It's not going to be a function by the vertical line test, right? So for this function, this is the end behavior. So y equals 1 is a horizontal asymptote. We're done. So the horizontal asymptote, I'll explain the slant in a minute, and end behavior. Symmetry, none. It cannot be symmetric if it has a vertical asymptote at -4. And the max-min, if we need to, we'll have to use the calculator. And now we're ready to graph this function. When we graph a function with asymptotes, we must start by graphing the asymptotes. So this function has 2 asymptotes. Can anyone give us those 2 asymptotes? X equals -4. Careful, we need the equation because otherwise we will not know what to graph. Indeed.
Y equals 1.
And y equals 1. Very good. All I need now, I don't care about anything, no explanations whatsoever, just the chart. So let's do this together and draw a conclusion. Okay, ready? From approaching 1, the function will go to positive infinity on the left-hand side of the vertical asymptote. One more time. From approaching 1, going up to positive infinity on the left-hand side of this
Then
vertical
wraps
asymptote.
around to negative infinity and then goes back up once it reaches
Not
the other
up.
side.
Not up.
Oh. Right.
So from negative infinity, we'll cross the y-axis at 0, -1/4. We'll cross the x-axis at 1, 0, and will eventually approach 1. So let's do the second part one more time. From negative infinity, It crosses the y-axis at 0, -1/4. It continues to cross the x-axis at 1, 0, and it will approach eventually 1 from below 1. That's all we need. Ready? So from 1 approaching infinity. No problem there. From negative infinity, so I have to plot these. 0, -1/4 will be something like here. And 1, 0 will be something like here. So from negative infinity, crossing the y-axis, crossing the x-axis, and eventually approaching 1 from below. This is the graph of x minus 1 over x plus 4, which is a rational function of type 1. With the graphing calculator, you have to be very careful because you need parentheses around the numerator and parentheses around the denominator, mandatory. So in parentheses, I have x minus 1 and divide by x plus 4. The calculator is not as smart as you are. It will not present another function that should be listed as what other function I need to graph. Okay. Yes, not the vertical ones, because I cannot plug in exactly. So what would that be in our case?
Y equals 1.
Thank you. Let's use the standard viewing window. See what happens. Nothing happens. Let me see if I can do it again because we didn't get the chance to see anything here. It doesn't allow me. I thought it was going to show us first graph and second graph. So as we expected, from approaching 1, going to positive infinity, from negative infinity, crossing at 0, -1/4, crossing at 1, 0, and approaching 1. Not touching. That's a lie. Not touching. That's how we graph type 1. Any questions before we continue to type 2? Any questions? Any questions?
I have none.
Okay. Anyone else other than Tom? Okay. So let's make one up or give me type 2. Any example you would like to work on of type 2?
X squared minus 4 over x plus 8.
That's type 3.
Oh.
So
just flip it then.
Okay. So the shortcut now for the horizontal asymptote for any function type 1. Here's the shortcut. What is the leading coefficient of the top? Make sure that they are in descending order. Otherwise, we may make a mistake in identifying the leading coefficient. So the leading coefficient is 1. What is the leading coefficient of the bottom?
1.
So the horizontal asymptote is y equals the leading coefficient of the top over the leading coefficient of the bottom. That's how we got y equals 1. However, I wanted to show you why that is. So that's why we went through this explanation. So if you want to remember it, you can, and using the shortcut. The horizontal asymptote for a type 1 is y equals leading coefficient. Oops, not 3f's. Leading coefficient of the leading coefficient. So if I have the example, let's say f of x equals 2x squared plus 1 over negative x squared minus 4, what will you say the end behavior and the horizontal asymptote will be for this function?
2.
Careful.
-2.
-2, right? The leading coefficient is 2. The leading coefficient is -1. So then the horizontal asymptote will be y equals -2. And the end behavior will be y.
That it approaches -2.
Yes, either from above or from below, not both. And that will be the end behavior as well. Very good. So let's look at a type 2. Let's say x plus 1 over x squared minus 1. By the way, is this type 2?
Yes.
Because the degree of the top is whatever, but the bottom has a degree higher. We don't care by how much. In type 3, we do care about how much. The top has to have degree 1 degree higher than the bottom. But here it doesn't matter. Good. What do you think I'm going to do first with this? Well, obviously, my starting point must be the domain. So then, obviously, what?
So wait, does that leading coefficient trick only work with type 1?
Yes.
I
This is easier.
could get away with it.
Yes, you can. So why is this? Why is this easier? Why is this easier? Because the top has so much less power than the bottom. So then at infinities, which one will grow faster, the top or the bottom?
The bottom.
Right. So it's the same concept. If the top is small and the bottom is big, the function will go where as x approaches infinity? 2?
Undefined. Or 0.
Top is small, bottom is very strong. I divided nothing by huge. So the end behavior for type 2 is always 0. The horizontal asymptote is always 0 for type 2. So this type 2 is much easier than type 1. But coming back to the beginning, so what do I do first? Okay, here's your hint. Exactly. Why do I need to factor the denominator? Because if I don't factor the denominator, I will not be able to find the domain. Right? I need the domain. Perfect. So x plus 1 over x minus, I should have waited. So what is the denominator? Say it again.
X plus 1, x plus 1.
Very good, thank you. How many restrictions do I have to state? Remember, I cannot touch it before I state restrictions. So what do I have to state first?
It cannot equal 1 and -1.
Very good. So x cannot be plus or minus 1. Now, I am allowed to do something, which didn't happen in the previous example because I specifically wanted something like this. So what am I allowed now to do? Say it again. It's already factored. Look at the expression, all this, and tell me what to do.
1 over x minus 1.
Say it again.
1 over x minus 1.
Thank you. So we are simplifying the same factor, top and bottom. And the simplified form of this fraction or expression, or if you want function, because that's what we are trying to do, is this. Awesome. Thank you. So now I can start my chart. What is the domain of this function? Oh, I didn't mean that. I meant to see where I'm at with them. Okay, 33. Again, what is the domain of this function, please?
-1.
Yes?
-1 to 1.
Awesome.
1 to infinity.
Excellent. So -1, 0, 1, infinity, and nothing here, and nothing here. Very good. Okay, now we have to discuss something happened here. Okay, which of the two factors disappeared?
Look, 1 and 1.
No,
Wait, x plus 1.
x plus 1. So under -1, I will say no vertical asymptote. X equals -1 whole in the graph. Which factor did not disappear and stayed in the final form of this function?
X minus 1.
which means that x equals 1 will definitely be. Thank you. So if a factor from the denominator disappears, the function is still undefined there, but there is no vertical asymptote there. It's a hole in the graph. If a factor stays in the denominator and does not go away with
like
the factor.
a piecewise function? I'm confused. I've just not heard that phrase before. Hole in the graph.
Yes, because the function is still undefined there, but it does not have a vertical asymptote. You'll see in a minute.
Okay.
So this one is a vertical asymptote because the factor stays in the final form. There's nothing I can do about it. So I know now the answer left and right. What I don't know is the sign of this infinity. Now I want to determine this. It's a hole in the graph. These cannot be infinities. So please plug in -1 in here and tell me what you get. I replace x
1
by
over
negative.
0, undefined.
Careful. So I replace x by -1 to see those values left and right. What are they? They have to be the same. So when I plug in -1, what do I get? In the denominator. But what is the value of the function?
1 over -2.
Right. So this is -1/2 and this is -1/2. Now, left and right of 1, I have to plug in 0.9 and 1.1 in order to identify the sign of the infinities. So let's plug in 0.9. Please tell me what happens when you plug in 0.9. What do we get? What is the sign? 1 over 0.9 minus 1. Sign.
Negative.
1.1 minus 1.
Positive.
Now, I'm also interested in x and y-intercepts. What happens when x is 0? What is the value of the function when x is 0? Very good, awesome. And now I'm going to ask you, when is this 0? When is the fraction 0? When is a fraction 0? When the numerator is 0. Is this numerator ever 0? No. So there is no y-intercept. There is no x-intercept because the numerator is never 0. Good. In the case of type 2, the end behavior is always 0. And y equals 0 is the horizontal asymptote. Can a function ever cross a vertical asymptote? I'm going to write this down for you, with you, if you want. Can a function ever cross a vertical asymptote? Never, ever possible. Can a function cross a horizontal asymptote?
Right.
It can. Here's the reason why it can. The horizontal asymptote is meant to tell us the end behavior. It's meant to tell us this piece where x goes to -infinity and this piece where x goes to +infinity. It has no meaning in the middle. But I cannot draw a horizontal line showing you a little piece here and a little piece here. I have to draw a horizontal line. So in between, in the middle, the function can cross it. Okay?
But it doesn't go further?
It will go to approach it. Yes, of course. That will not change. So let's write it as a note. A function, a rational function. I should write rational. A rational function can cross a horizontal asymptote. I'm going to put in parentheses also, but we haven't talked about it yet. A slant asymptote, comma, but never, ever what?
Vertical asymptote.
A vertical asymptote. Correct. So a function can cross a horizontal asymptote. It can cross a slant, but it will never ever cross a vertical asymptote. Good. So now let's try and make sense of this information and graph the function. Ready? From approaching 0, the function will decrease, and at -1, -1/2, it has an open point. It will cross the y-axis at 0, -1, and approach -infinity on the left-hand side of the vertical asymptote. One more time. From approaching 0, below 0, we'll cross this at this point, go through this point, -1, -1/2. We'll cross the y-axis at 0, -1, and then go to -infinity. On the other side, the function will start at positive infinity and approach 0 eventually from above. That's it. So when we graph a function with asymptotes, what do we have to graph first?
The horizontals.
The horizontal is an overkill because it's already there. And what else?
The
Vertical asymptote, which is x = 1.
and the horizontals.
It only has one, y = 0. And I will plot this point, -1, -1/2. -1, -1/2. I will also plot this point, 0, -1. And again, I'm back to my chart. From approaching 0, from below, because it doesn't have any x-intercepts. So going through this point, crossing the y-axis, and then approaching -infinity. That's what I have here. On the other side of the vertical asymptote, from positive infinity, going down to 0 from above. And one item that Tom recommended, and I forgot to ask you here, he said, let's also find the range of this. Why not? Can anyone give us the range?
I just thought that we found the domain.
You are right. You're right. Let's find also the range for this function. Can anyone give us the range of this function?
All real numbers except 1.
Thank you. So it will be -infinity 1 union 1 infinity. Very good. Awesome. Thank you. Everything except 1. Perfect. Now, can anyone, so this is the function f of x, which is x + 1 over x squared minus 1. Can anyone give us the range for this function?
All real numbers except 0. Right?
X is greater than 1.
Let's do this together. Let's do this together.
Let me see.
Yes, 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 no. Yes, 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 no. Yes, yes, yes,
Oh,
yes,
I see.
yes.
Okay, so I think I get it now. All real numbers except 1 and 0. Right? -1 and 0.
Okay, this point is at -1/2. -1, -1/2, and we are talking about the range.
Right. So, all real numbers except 1/2 and 0. Right?
-infinity 0, 0.
Not 0.
-1/2.
-infinity to -1/2 union, comma,
Infinity?
union,
That's what
0 to infinity.
I feel like I said that, like, all real numbers except, no, I didn't say -1/2, right?
Yes,
You got me there.
you are close. With the graphing calculator, please. Okay, in y = clear. In this particular situation for type 2, there is no need for writing y = 0 because that's the x-axis anyway, so it will be graphed no matter what. So parentheses always for the top and the bottom. We had x + 1 and divided by x squared minus 1. Let's think about the viewing window. Standard viewing window should be okay.
Should.
It's not going to be sufficient, but let's say graph. Here it comes. Here it comes. We know the graphing calculator is lying. So this function does not touch the x-axis. This function does not touch the x-axis. The other lie that the calculator is telling us is this point here at -1, -1/2. It's an open point. So I'm going to try and show you by zooming in, really zooming in. So I'm going to change the x minimum to -2 and x maximum to 0 with a scale of 0.5 and y minimum -1, y maximum 0, because I wanted to see that blip. Here it is, blip. That little blip right here. It's an open point, not a vertical asymptote. If it were a vertical asymptote, 1, 2, 3, or 4, but that's not the case.
So it just breaks there?
It just breaks the graph, exactly. Yeah. Very good. Okay, type 3. Because I like to look at some applications of rational functions. Okay, type 3. Can anyone invent a type 3 for us?
Well, I inadvertently did last time,
Yes.
but I don't remember it.
Okay, here it is. So this is type 3. F of x equals x squared minus 9 over x plus 1. Now I'm going to ask you, I know I repeat myself a lot, is this type 3? Yes, because the degree of the top is
1 greater than the bottom.
awesome. I couldn't have said it better or easier. Excellent. Thank you. Good. I get my chart going where I put all the information. What is the starting point, no matter what?
Negative infinity, right? On the left-hand side, or 0.
What else should I do here right away? Thank you very much. Good. So can anyone give us the domain of this function?
I want to say all real numbers except 1.
Let's plug in 1 and see if we can determine an output.